It was internet consultant Michael Monker who said if the automobile had followed the same development cycle as the computer, a Rolls-Royce would today cost $100 and get 1,000,000 miles per gallon. In this lesson, we're going to write, interpret, and graph a straight line depreciation equation, all to answer the question, what is the value of your car? Before we begin, let's make sure we're ready for this lesson by answering warm-up number 2. Now, you can use a graphing calculator, graphing software, or a spreadsheet to find the 2-point of intersection of the exponential equation 100 times 1.2 to the x power and y is equal to negative 125x plus 4,000. When you do this, you're going to find the point of intersection is at 16.3 and 1960. Now, let's take a look at a problem you will be able to do by the end of this lesson. Suppose that your car straight line depreciates monthly over time. You know that after 12 months, your car is worth $24,600. According to an online car value calculator, after 23 months, your car is now worth $21,850. How much does the car depreciate each month? The problem can be modeled using an arithmetic sequence. Recall from our section on banking services that an arithmetic sequence is a progression in which any two consecutive numbers have a common difference. If you were to list the car values as a sequence, the common difference would be represented by the monthly depreciation amount. The term A sub 12 represents the car value at 12 months, and A sub 23 represents the car value at 23 months. Let A sub 12 equal 24,600 and let A sub 23 equal $21,850. The formula for any number A sub n in an arithmetic sequence is given by A sub n is equal to A sub 1 plus n minus 1 times d, where d is the common difference. So with that, we can see that the A sub 12 will give us 24,660 is equal to A sub 1 plus 12 minus 1 D, and that the A sub 23 will give us 21,850 is equal to A sub 1 plus 23 minus 1 times D. We can simplify both of these so that we get the first one being 24,600 is equal to A sub 1 plus 11D, and 21,850 is equal to A sub 1 plus 22D. Let's subtract this whole second equation from the first equation, allowing us to eliminate the A sub 1s and be left only with the D. That's going to give us 2750 is equal to negative 11D, or that negative 250 is equal to D. So the common difference is a negative 250. This can be interpreted as a drop in the car value of $250 every month. Most cars depreciate. That is, their value becomes less than their purchase price over time. Some collectible cars increase in value over time or appreciate. The simplest form of depreciation is straight line depreciation. When a car loses the same amount of value each year, the scatter plot that models this depreciation appears linear. In reality, cars do not depreciate by the same amount each year. But when calculating depreciation for the IRS tax forms, linear depreciation formulas are used. Therefore, we begin this lesson by examining linear automobile depreciation. By determining the equation of the linear model, you can find the value of the car at any time in its lifespan. There are many factors contributing to the depreciation of an automobile. The condition of the car, mileage, and the make of the car are only a few of those factors. The straight line depreciation equation is a mathematical model that can be used as a starting point in examining auto depreciation. In previous math courses, you used the intercepts of linear equations when graphing linear functions. Traditionally, the horizontal axis is called the x-axis and the vertical axis is called the y-axis. Both the x-intercept and the y-intercepts are numbers, not coordinates. The locations on the graph of the horizontal x-intercept always is in the form a, 0, and the location on the graph of the vertical or y-intercept always has the form 0, b. In addition to intercepts, straight lines also have slopes. The slope of the line is the numerical value for the inclination or declination of a line. It is expressed as a ratio of the change in the value of y over the change in the value of x, forming the point on the line after another point. Using those variable names, the slope of a line would be represented by the following ratio. The slope is equal to the change in y divided by the change in x. If the coordinates of the 2 points are x sub 1, y sub 1, and x sub 2, y sub 2, then the slope can be modeled mathematically with this ratio. The slope ratio is equal to y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. The independent variable in the car's depreciation equation is time in years, and the dependent variable is the car value. By identifying the intercepts and slopes of a straight line depreciation model, you'll be able to determine the equation that represents the depreciation. Here we're going to learn how to find the straight line depreciation equation. Suppose that you purchase a car for $27,000. According to your online research, this make and model of car loses all of its marketable value after 12 years. That is, it depreciates to a value of $0 12 years after the purchase date. If this car depreciates in a straight line form, what are the coordinates of the intercepts of the depreciation equation? So if we let x represent the time in years, the minimum x value is 0 years, the purchase year of the car. Because the car totally depreciates after 12 years, the maximum value will be 12. A straight line depreciation equation, the coordinates of the intercepts are 0, max value of car, and maximum lifespan, 0. Let y represent the value of the car at any time during its lifespan. The minimum y value of $0 and maximum y value of the purchase price of $27,000. Knowing this information, you can identify the coordinates of the intercepts as 0, 27,000 and 12, 0. Now let's check our understanding of this. A car sells for D dollars and depreciates to a value of 0 after T years. If the car straight line depreciates, what are the coordinates of the intercepts of the straight line depreciation equation? Well, this is fairly easy because we get a 0, capital D, and we get a capital T, 0. Determine the slope of a straight line depreciation equation for the situation from example 1. 2 points determine a line, so you only need 2 points to determine the slope of the line. Let the coordinate of the y-intercept be the first point. That is that x sub 1, y sub 1 will equal 0, 27,000. Let the coordinates of the x-intercept be the second point. This would be x sub 2, y sub 2 being equal to 12, 0. So if the slope m is equal to y2 minus y1 over x2 minus x1, then we get 0 minus 27,000 divided by 12 minus 0, which would give us a negative 27,000 divided by 12, which is equal to a negative 2,250. Now let's check our understanding and write a slope for a straight line depreciation equation that models the situation in which a car is purchased for D dollars and totally depreciates after T years. Well, we know that x sub 1, y sub 1 would be 0, d, and x sub 2, y sub 2 would be t, 0. So m would be our y2, which is 0, minus our y1, d, all over our x sub 1 t minus 0. This would give us a negative d over t. Now let's graph some straight line depreciation. Write a straight line depreciation equation for the situation discussed in example 1 and 2, then draw the equation. The general form for the equation of a straight line is y equals mx plus b. where m is represented by the slope and b represents the y-intercept. And we already know that m, the slope, is negative 2250. And we already know that the y-intercept b is 27,000. This means our y equals mx plus b would be y equals negative 2250x plus 27,000. So on our graph, the x-axis is time in years and the y-axis is dollars. We would be able to put 27,000 up as the y point and 12 as the x point. Connecting these with a straight line will show us the graph. Now let's check our understanding of this. Write and graph a straight line depreciation equation for a car that was purchased for $22,000 and totally depreciates after 11 years. I tend to start by making a graph before I make an equation. I know that the y-axis is dollars and the x-axis is years. It will totally depreciate after 11 years, and it started at $22,000. Being a straight line depreciation, I now have these 2 points. This means that my m is my change in y, which is 22,000, divided by my change in x, which is 11. This means I have a slope of negative 2,000. Now, I know that I don't see a negative here, but this is going down in value. And you could be more mathy about it by saying 0 minus 22,000 divided by 11 minus 0. That would show you the negative. Just did it in a little bit more of an intuitive way. It also gave us very clearly the y-intercept b being 22,000. So our y equals mx plus b would be y equals negative 2,000x plus 22,000. Suppose Jack purchased a car 5 years ago at a price of $27,600. According to research on this make and model, similar cars have straight line depreciation to zero value after 12 years. How much will Jack's car be worth after 66 months? I start by making a graph and understanding that things end at 12 years. This is my time in years on my x-axis, and everything began at $27,600 on my y-axis. So my slope m would be negative 27,600 divided by 12. This means I have a negative 2,300 slope. It already gave us our y-intercept of 27,600. So y is negative 2300x plus 27,600. 66 months, this is our time. This is our X number that's going in. But since it's months and we're measuring in years, I need to say 66 divided by 12 is 5.5 years. This is going to become my X value. So Y is negative 2,300 times 5.5 plus 27,600. This means the car will be valued at $14,950 after 5.5 years. Let's check our understanding of this. A car sells for $18,495 and straight line depreciates to zero after 9 years. Write a straight line depreciation equation for this car and the expression for the value after W months. Well, the y-intercept is going to be the 18,495. The x-intercept will be at 9 years, giving us our graph and our line. So m will be negative 18,495 divided by 9. That's going to be a negative 2,055. The y-intercept is already known to us, meaning that y is negative 2055x plus 18,495. Now we want to know about W months, but X is measured in years. So what we're going to do is say negative 2055. Now that W divided by 12 will convert months into years and add 18,495. A straight line depreciation equation for a car is Y is equal to negative 4,000X plus 32,000. In approximately how many years will the car's value reach 25%? The original value of the car is the y-intercept of 32,000. You must determine the actual value of the car after it dropped 25%. This can be done in one of two ways. You can find 25% of the original value of the car and then subtract that amount from the original amount. So 0.25 times 32,000, that's going to give us 8,000. This means what we're looking at is a $24,000 vehicle. So when is the value $24,000? Or we could notice that once the car drops in value 25%, it will be worth 75% of its original value, meaning 0.75 times 32,000 and get 24,000 in that way. Regardless, we're going after the same number. Now we're trying to determine the length of time. So we're going to solve this depreciation equation for X, meaning 24,000 is equal to negative 4,000x plus 32,000. Moving 32,000 to the other side, changing its sign, we have a negative 8,000 is equal to negative 4,000x, meaning 2 is equal to x when we divide both sides by negative 4,000. So the car will depreciate by 25% after 2 years. Now let's check our understanding of this and write an algebraic expression that represents the length of time it'll take a car from the last example to have a value of d dollars. We're going to start with this idea of y is mx plus b, and we're going to solve it for x, meaning we're going to say y minus b is equal to mx, or y minus b divided by m is equal to x. Now, we already know a great deal of information from that last question. Here, our unknown end value is d. If we subtract the original purchase price of $32,000 and divide it by its depreciation of a negative $4,000, then we'll be able to find that answer. In all the previous examples, we worked with depreciation functions to determine the value of a car at a given point of time. You know how to examine expense functions that will indicate the cumulative amount of money spent on any given point in time. You can create an expense function for an automobile. While there are many expenses that contribute to the running and upkeep of a car, for the purposes here, the expense function will be composed of the fixed expense down payment that you make when you purchase the car and the variable expense monthly payment that you make to the lending institution. Look at the linear expense and depreciation functions simultaneously, and that will give you insight into the value of your automobile investment. Celine bought a new car for $33,600. She made a $4,000 down payment and pays $560 each month for 5 years to pay off her loan. She knows from her research that the make and model car she purchased has a straight line depreciation to zero after 10 years. So we want to create an expense and depreciation function, graph these functions on the same axis, and interpret the region before and after the intersection points. Let X represent time in months and Y represent dollars. Celine's expense function is the sum of her monthly payments over time, $560, and her initial down payment of $4,000. So we're going to wind up with Y is 560, her monthly payment, times the number of months, plus $4,000, her down payment. Since the time X is in months rather than years, we're going to need to express her depreciation function in terms of months as well. Celine's car totally depreciates after 10 years, or 120 months. To determine her monthly depreciation amount, divide the original car value by 120. So 33,600 divided by 120 gives us 280. So Celine's car depreciates $280 per month. To calculate the slope of the depreciation equation, we're going to use the coordinates to interpret. So we have 0, 33,600 and 120, 0. This means we're looking at our y sub 1 minus y sub 2 over x sub 2 minus x sub 1, or 0 minus 33,600 over 120 minus 0, giving us a negative 33,600 over 120, which gives us a negative 280. The slope of the depreciation equation is a negative 280. Notice that the slope is the negative of the monthly depreciation amount. The straight line depreciation function of Celine's auto would be y equals negative 280x plus 33,600. So now we have created an expense and depreciation function. Let's graph these functions on the same axis. So we know that it started in value at 33,600 and its value is 0 at 120 months, giving us our first line fairly easily. Now, she started with a $4,000 down payment and she made a payment every single month of $560, meaning this point right here is where things get to intersect. So we have these two y equations and we can set them equal to each other so that 560x plus 4,000 would be equal to negative 280x plus 33,600. This is going to give us 840x is equal to 29,600, or that x is equal to 35.24. Knowing that x is equal to 35.24, we can use either of these equations to figure out the y value. So if we said y is equal to 560 times 35.24 plus 4,000, then y would be equal to $23,734.40. This means a little bit after more than 35 months, both Celine's expenses and her car value are the same. In the region before the intersection point, the expenses are lower than the value of the car. In the region after the intersection point indicates the period of time that the value of the car is less than what she has invested into it. Let's check our understanding of this. How might the expense function be altered so that it reflects a more accurate amount spent over time? And what effect might this have on the graph? Well, you could include your monthly maintenance and insurance costs with the monthly payment amount. This will yield a slope that is greater than the one depicted in the graph. Since the expense graph will be steeper, the intersection point will have an x value that is less than 35.24. This will indicate that the value of the car will be less than the expenses to date earlier in the car's lifetime. Suppose that your car straight line depreciates monthly over time. You know that after 12 months, your car is worth $24,600. According to an online car value calculator, after 23 months, your car is now worth $21,850. How much does the car depreciate each month? The problem can be modeled using an arithmetic sequence. Recall from our section on banking services that an arithmetic sequence is a progression in which any two consecutive numbers have a common difference. If you were to list the car values as a sequence, the common difference would be represented by the monthly depreciation amount. The term A sub 12 represents the car value at 12 months, and A sub 23 represents the car value at 23 months. Let A sub 12 equal 24,600 and let A sub 23 equal $21,850. The formula for any number A sub n in an arithmetic sequence is given by A sub n is equal to A sub 1 plus n minus 1 times d, where d is the common difference. So with that, we can see that the A sub 12 will give us 24,660 is equal to A sub 1 plus 12 minus 1 D, and that the A sub 23 will give us 21,850 is equal to A sub 1 plus 23 minus 1 times D. We can simplify both of these so that we get the first one being 24,600 is equal to A sub 1 plus 11D, and 21,850 is equal to A sub 1 plus 22D. Let's subtract this whole second equation from the first equation, allowing us to eliminate the a sub 1's and be left only with the d. That's going to give us 2750 is equal to negative 11d, or that negative 250 is equal to d. So the common difference is a negative 250. This can be interpreted as a drop in the car value of $250 every month. Let's check our understanding of this. A car straight line depreciates monthly over time. After 8 months, the car is worth $29,520. After 18 months, the car is worth $26,420. How much does this car depreciate each month? So we have our a sub 8 to start with. And a sub 8 is equal to $29,520. We already know that this is going to give us $29,520 is equal to a sub 1 plus 8 minus 1 times d. A sub 18 will give us 26,420, so that's going to supply us with the equation 26,420 is equal to a sub 1 plus 18 minus 1 times d. Simplifying both equations, 29,520 is equal to a sub 1 plus 7d, and 26,420 is equal to a sub 1 plus 17d. We'll subtract the entire second equation from the first. This will give us 3,100 on the left and a negative 10d on the right. So negative 310 is equal to d. So the common difference is a negative 310, and that means the car depreciates $310 every month.